All right, are you ready to dive deep into self-healing
Oh,
materials?
absolutely.
We've got some really interesting stuff on heavy water today.
Yeah.
Self-healing concrete
Uh-huh.
and smart
It's
polymers.
going to be fascinating.
It really is. The future of materials science. It's pretty wild what's happening.
It really is remarkable. It's like this convergence of totally different fields, you know?
Yeah.
You've got heavy water, which can actually disrupt cellular processes. It's
Mhm.
almost like an anti-healing effect.
Right.
And then on the other end of the spectrum, concrete that mends its own cracks.
It's a paradox, isn't it?
Yeah.
Like water, it's essential,
Right.
but in a different form,
Yeah.
it can just totally mess up our cells.
It throws a wrench in the whole system.
Yeah.
And then concrete, which you think of as this rigid, unyielding material,
Yeah.
it's suddenly adaptable, self-referring.
Exactly. And that's where these smart polymers come in.
Yeah.
The materials that actually change their properties in response to the environment.
It's amazing.
It's like they're blurring the lines between living organisms and inanimate matter.
That's a great way to put it.
Okay, let's break this down a bit. You said heavy water disrupts cellular processes.
Uh-huh.
For those of us who didn't, get a PhD in chemistry,
Yeah.
what makes heavy water different from regular water?
It all boils down to the hydrogen atoms.
Oh, yeah?
Regular water, H2O, 2 hydrogens, 1 oxygen.
Yep.
But in heavy water, the hydrogen atoms are replaced with deuterium.
Okay.
It's a heavier isotope.
Hmm.
So it's still H2O, but with a slightly different mass.
So it's like a tiny tweak to the molecule,
Right.
but with huge consequences.
Huge consequences. That difference in mass means heavy water interferes with all sorts of delicate processes.
Yeah.
Cellular signaling, even DNA replication.
It's like trying to
Yeah,
run a finely tuned machine with the wrong type of oil.
exactly.
Things just start to break down.
It throws everything off.
That's fascinating. It makes you realize how sensitive our cells are to even tiny changes.
They really are.
And it's interesting how scientists can use those tiny disruptions to actually study the processes themselves.
Right.
It's like a back door into understanding how cells work.
Exactly. By observing how heavy water messes things up, researchers can learn a lot about how cells function normally. And potentially, they can develop new therapies based on that knowledge.
It's a powerful tool for scientific discovery.
It really is.
So we've got this anti-healing effect of heavy water.
Uh-huh.
Now let's go to the opposite end, self-healing concrete.
Okay.
I have to admit, the idea of concrete repairing its own cracks
Yeah.
sounds like science fiction.
It's pretty amazing.
How does that even work?
Well, there are a couple of approaches.
Okay.
One uses bacteria.
Bacteria.
Yeah, you embed them right into the concrete. And these bacteria, they produce calcium carbonate.
Okay.
That's basically the same stuff that makes up seashells.
So the concrete has its own little repair crew.
That's one way to think about it.
What makes the bacteria start producing the calcium carbonate?
Well, when a crack forms,
Hmm?
it exposes the bacteria to air and moisture.
Okay.
That activates them,
Oh.
triggers the production of the calcium carbonate.
So they fill the crack with their own healing material.
That's right.
It's like the concrete is copying nature's own repair mechanisms.
Yeah, it's biomimicry in action.
What's the other method?
The other method uses tiny capsules
Okay.
filled with a special healing agent.
Uh-huh.
These capsules get mixed into the concrete,
Yeah.
and when a crack forms, the capsules break open. They release the healing agent.
It's like a self-administered bandage.
Exactly, a little first aid kit for the concrete.
It's a brilliant idea, these approaches.
They are.
But I imagine there must be some challenges, right?
Oh, absolutely.
Implementing this stuff on a large scale.
Yeah.
What kind of challenges?
Well, one of the main ones is cost. Self-healing concrete, it's still pretty new
Yeah.
and more expensive to make than traditional concrete.
Mhm.
But as the technology develops, we can expect the costs to come down.
Sure. And I guess in the long run,
Right.
the savings in maintenance and repair
Absolutely.
could make self-healing concrete the way to go.
Yeah, especially for big infrastructure projects.
Bridges, roads.
Exactly. It could save a lot of money and hassle in the long run.
And it's not just about the money.
Right.
Self-healing concrete could lead to safer structures, too.
Absolutely. Yeah. More durable.
Less risk of those catastrophic failures.
Right.
So it's a compelling argument
Definitely.
for investing in this technology.
It's a smart investment for the future.
It's like we're moving towards this future where our infrastructure, it isn't just static. It can adapt and heal over time.
Yeah, it's a whole new way of thinking about how we build things.
That's where these smart polymers come in.
Right.
They represent a whole different way of looking at materials.
Yeah.
Like we're not just designing materials for their passive properties anymore.
Right.
We're figuring out ways to make them responsive, adaptive.
It's a paradigm shift.
So smart polymers are the next level of self-healing materials.
In a way, yeah. Self-healing concrete, it's designed to solve one specific problem.
Yeah.
Cracking.
Right.
Smart polymers are much broader.
I'm listening. What makes smart polymers so special?
They're materials that change their properties
Okay.
based on the environment they're in,
Hmm.
temperature changes, light, even mechanical stress.
So they can sense changes,
Yeah,
react
they
accordingly.
have this built-in sense and response mechanism.
Hmm.
It's pretty amazing.
Okay, I think I'm starting to get it. But can you give me some examples? Real-world applications.
Sure. A fascinating example is shape memory alloys.
Shape memory alloys.
Yeah, like nitinol, you can deform a nitinol object,
Okay.
but when you heat it up, it remembers its original shape.
Wait, really? It just goes back?
Snaps right back.
How's that even possible?
It's all about the molecular structure.
Hmm.
Nitinol has this unique structure that lets it exist in two different crystal phases.
Okay.
At lower temperatures, it's in a more flexible phase.
Ah.
But when you heat it up,
Uh-huh.
it transitions to a more rigid phase, which causes it to spring back to its original shape.
That is incredible. I could see how that would be super useful in all sorts of applications.
It is. Shape memory alloys are being used in everything from medical implants to eyeglasses.
Like what?
In medicine, for example, they use them in stents.
Hmm.
Tiny tubes they insert into blood vessels
Yeah.
to open up blockages.
Huh.
The stent starts in a compressed form,
Okay.
and then it expands to open up the blockage.
So it's like these futuristic materials are already being used in really practical ways.
Yeah, the future's already here.
It really is. It makes you wonder what else is on the horizon.
Oh, the possibilities are endless. Researchers are looking at all sorts of things.
Like what?
Using smart polymers in drug delivery systems, for example.
Hmm.
They could release medication in a very controlled and targeted way.
Wow.
And then there's self-healing textiles.
Self-healing textiles.
Fabrics that can repair themselves.
So you'd never have to throw out a ripped shirt again.
That's the idea. Clothes that can mend their own rips and tears.
Amazing. It sounds like we're on the verge of a materials revolution.
We are. It's a very exciting time to be in this field.
I can only imagine, like our everyday objects,
Yeah,
becoming more durable,
right.
adaptable,
Uh-huh.
responsive to our needs.
And it all stems from this fundamental shift in how we think about materials science.
We're going from those static, passive materials
Right.
to a future where materials can sense, react, even heal themselves.
It's a whole new world of possibilities.
This is pretty mind-blowing stuff. I'm starting to see how these different concepts are all connected.
How so?
Well, we started with heavy water,
Uh-huh.
which shows us how even the smallest molecular changes can have these huge consequences.
Right.
Then we have self-healing concrete,
Hmm.
which is like this targeted application of adaptable materials.
Yeah.
And finally, there are smart polymers,
Right.
which represent this underlying principle of designing materials to react to their surroundings.
Exactly. It's not just about passive properties anymore. It's about active response.
Yeah, they don't just exist, they respond.
They interact with their environment.
We're only just scratching the surface of what's possible with self-healing materials.
It's a field with incredible potential.
I can't wait to delve deeper into this. But before we move on to the next part of our deep dive,
Yeah.
let's just recap quickly for our listeners of what we've covered so far. We talked about heavy water and its disruptive nature,
Hmm.
the ingenious ways that concrete can now mend itself,
It's pretty remarkable.
and the fascinating world of smart polymers.
It's a whole new frontier in materials science.
It really is. This is just the beginning of our exploration into the world of self-healing matter.
There's so much more to discover.
Join us in the next part of our deep dive as we delve further into the science, the applications, and the potential impact of these incredible materials.
It's going to be fascinating.
It really is. I can't wait. Me too.
Welcome back to our deep dive into self-healing materials.
It's pretty amazing to think about the potential, right?
It is.
Safer buildings, medical implants that actually work with the body.
Absolutely. And that's where biocompatible materials come in.
Okay, biocompatible materials. That sounds futuristic. What do we talk about here?
Think about medical implants,
Okay.
but ones that integrate seamlessly with the human body.
Hmm.
We're not talking about inert pieces of metal or plastic.
Right.
These are designed to actually interact with our tissues.
At a molecular level.
Exactly.
So these implants wouldn't just replace damaged parts.
Right.
They could actually encourage healing,
They could, yeah.
maybe even regeneration.
Exactly. Imagine an artificial heart valve.
Okay.
It not only functions properly, but encourages new blood vessels to grow.
Hmm.
And it integrates perfectly with the surrounding tissue.
Wow, that would be a game changer. No more worries about rejection
Right.
or needing multiple surgeries as you grow.
It would be a huge step forward.
What other possibilities are there with biocompatible materials, I mean?
The possibilities are pretty much endless. Researchers are exploring everything from artificial organs to bone grafts.
Wow.
Even skin substitutes that can heal and regenerate just like our own tissues.
It's incredible to think we could one day repair or even replace damaged organ
Yeah.
with materials that actually mimic the body's own healing processes. Amazing. What are the biggest challenges in developing these materials?
Well, one of the biggest hurdles is understanding the complexity of living tissues.
Yeah, our bodies are pretty intricate systems.
They are incredibly complex. Creating materials that integrate seamlessly is a huge challenge.
I can imagine. It's like trying to create a perfect replica of a masterpiece.
It is. And another challenge is safety, making sure these materials are safe and effective in the long term.
Of course, we don't want them to break down over time.
Right, or trigger any adverse reactions.
So how are scientists approaching this? What are some of the breakthroughs driving progress?
One key area of research is dynamic covalent chemistry.
Dynamic covalent chemistry, okay.
Remember we talked about reversible bonds in smart polymer?
Yeah, I remember.
That kind of chemistry is really important for biocompatible materials.
So,
It's all about creating materials that can adapt
hmm,
and respond to their surroundings,
okay.
just like living tissues do.
So how do these dynamic covalent bonds work?
Dynamic covalent bonds allow materials to break
Okay.
and reform in response to certain stimuli.
It's like they have tiny switches
Exactly.
that could be flipped on and off,
Right.
allowing the material to change its properties.
That's a great way to put it.
And this is what makes dynamic covalent chemistry so important.
It is. It's the key to creating materials that can self-heal, adapt to changes in the body, and even interact with cells.
On a molecular level.
Exactly. It's like giving these materials a sense of touch and the ability to react accordingly.
I see. That's what makes them so promising for these biocompatible applications.
Absolutely. Dynamic covalent chemistry is opening up a whole new world of possibilities.
So we've got these incredible biocompatible materials on the horizon.
We do.
But what about applications beyond medicine?
Well, there are plenty.
You mentioned smart textiles earlier. Anything new happening there?
Absolutely. Smart textiles are really taking off. Researchers are developing fabrics that can do all sorts of amazing things.
Like what?
Well, for example, regulate temperature,
Okay.
repel water,
Hmm.
even change color on demand.
Wait, what? Change color?
It's like having clothes that can adapt to any situation.
That's amazing. I'm picturing a jacket that keeps you warm in the winter, but then turns into a light windbreaker when it warms up.
That's the idea, and it goes far beyond just temperature regulation.
Like what?
Imagine clothes that monitor your vital signs
Hmm.
or alert you to potential health issues.
Wow.
Even administer medication through the skin.
If like clothing and technology are becoming one.
They are, and that's what makes this field so exciting. We're seeing this convergence of materials, science, biology, and technology.
Leading to all sorts of amazing innovations.
Exactly. Innovations that could revolutionize the way we live.
It's mind-boggling to think about. What other areas are researchers looking at with smart textiles?
Another promising area is in self-healing fabrics.
Self-healing fabrics.
Yeah. Imagine clothes that can repair rips and tears on their own.
Okay, now that would be incredible. I'm always throwing out clothes because of a little rip or snag.
It would be a game changer. Extend the lifespan of our clothes.
Reduce waste.
Exactly.
Are there any other applications for smart textiles that you're particularly interested in?
One area I find particularly fascinating is wearable electronics.
Wearable electronics.
Imagine integrating sensors and displays, even computing power, right into our clothing.
That's wild. What could we do with that?
It could revolutionize everything from fitness tracking to communication, even healthcare.
It's like technology becomes a part of us.
It would be seamlessly integrated into our lives, almost like a second skin.
It's incredible to think about the possibilities.
Smart textiles are really paving the way for a whole new future.
This is really fascinating stuff. It seems like we're only beginning to scratch the surface of what's possible.
We are. There's so much more to come.
What are you most excited about? What are the next big things in this field?
Well, one area that I find particularly exciting is the development of 3D printed molecules.
3D printed molecules. What's that?
It's a technology that lets us create materials with incredibly precise structures and properties.
Wow.
It opens up a whole new world of possibilities for designing self-healing materials.
So we could basically design and build materials from scratch, atom by atom.
Exactly. That level of control is amazing.
So we could make self-healing materials that are perfectly suited for any application.
That's the idea. Imagine a biocompatible implant that integrates seamlessly with the body.
Yeah.
Or a self-repairing aircraft wing that can withstand incredible stress.
The possibilities are endless.
They really are. It feels like we're on the verge of a new era in material science.
I think you're right. But it's important to acknowledge that these advancements don't come without challenges.
You're absolutely right.
Potential downsides,
You
too.
have to be mindful of those.
Cost is a big one, right?
Absolutely. Self-healing materials are often more expensive to produce than traditional materials.
Yeah, which could limit their accessibility and impact.
Exactly. It raises questions about equity and fairness.
We want to make sure everyone benefits from these advancements.
Exactly. Not just those who can afford it.
It's a societal issue as much as a scientific one.
Absolutely. And we also need to consider the environmental impact.
Yeah, that's important. Making sure the production and use of these materials don't create new environmental problems.
We want to contribute to a more sustainable future.
Right, not create more problems.
Exactly. While these materials have potential for sustainability, we have to be mindful.
Of their entire life cycle.
Absolutely. From raw materials to end-of-life disposal.
We don't want to solve one problem just to create another.
That's right. It's important to approach this technology with a holistic perspective.
Yeah, thinking about its impact on both the environment and society.
We need to have open and honest conversations about these issues.
With scientists, policymakers, industry leaders, everyone.
Absolutely. The public, too.
It's been an incredible deep dive so far. We've explored so much.
It has been fascinating.
Biocompatible implants, smart textiles, even 3D printed molecules.
We've only just begun to explore the possibilities.
And we've touched on the challenges.
Right, the ethical considerations.
As this technology keeps evolving, join us for the final part of our deep dive. We'll go even deeper into the impact these materials could have.
It's going to be a thought-provoking discussion.
Welcome back to our final part of this deep dive into self-healing materials.
It's been quite a journey exploring all the science and the potential applications.
We've covered so much, from how heavy water affects cells to self-healing concrete, and those incredible smart polymers.
Yeah.
We even got into biocompatible materials.
Right. The potential for medical implants that work with the body. It's amazing.
But now I'm thinking, what about the bigger picture? Like, what happens when this stuff becomes normal?
Interesting question.
How could it change our relationship with, the things we use every day?
Well, that's something a lot of people are thinking about. Researchers, futurists, one big change could be in how we consume things.
I see what you mean. If things last way longer because they can heal themselves.
Exactly.
That really challenges our whole throwaway culture.
It does. Imagine your phone or even your car lasting decades.
Not just a few years.
Right. It would turn our current economic model on its head.
Because everything's based on buying new stuff all the time.
We have to rethink our whole relationship with material possessions.
Maybe we'd move away from mass production.
It's possible, more localized, sustainable manufacturing.
And put more emphasis on fixing things, refurbishing, instead of just tossing them out.
That could create whole new industries, jobs focused on keeping products running.
Wow. It's amazing to think how this could change the economy. And what about the environment?
Oh, huge potential there. Imagine fewer landfills.
Less pollution.
A truly circular economy where materials are constantly reused and repurposed.
That's a goal worth working towards. But like any powerful technology, there are risks, ethical things we have to consider.
You're absolutely right. We have to develop and use these materials responsibly.
Think about the long term, the unintended consequences.
Exactly. For example, what if these materials end up in the environment?
Could they cause problems we haven't even thought of?
It's a legitimate concern, and researchers are working on it. They're developing materials that are biodegradable or can be safely recycled.
That makes sense. And what about, misuse? Could someone make things too durable?
Too durable.
So they never break down. We end up with even more waste, just a different kind.
That's another important point. We need that balance. Durability, but also sustainability.
So things are designed with their whole lifespan in mind.
From the very beginning to the very end.
These are big questions. We need to really think them through.
We do, and it requires open discussion.
Scientists, policymakers, industry folks, the public.
Everyone needs to be involved.
It's been an incredible deep dive. We've learned about the amazing possibilities of self-healing materials.
From tiny implants to smart clothes and even 3D printed molecules.
And we've talked about the challenges, the things we need to be careful of.
It's a complex issue, but one with huge potential.
I feel like I've learned so much, inspired too, and ready to, be a part of this change.
I feel the same way. It's been a great discussion.
And to our listeners, thanks for joining us on this journey into the future of materials. Self-healing matter, it's full of possibilities.
We can't wait to see where it takes us.
Keep exploring, stay curious, and let's build a future where things can heal and adapt.
Just like the natural world around us.
That's it for our deep dive today. Thanks for listening.